Alrighty, so let's go ahead and get this thing done here. We have a couple types or a couple problems to work, and then I want to show you a couple things about how to come up with your post-lab answers for your electrochemistry lab. Because honestly, the purpose of that lab was just more to have fun with it. Making a cell, see what it looks like, see what kind of issues there are. Making a cell, explain why this thing spends so much money on batteries, because they're not that hard to make, except that your data would, and if your data's not very good, it's because apparently you have to be a little more careful when you make them. All right, can everybody see okay?
Yeah.
Okay, not before we finish the new stuff. We can go back, but that's stuff that we need to do. All right, well then we'll definitely be looking at that. All right, can everybody see okay? All right, you will find if you pull out one of the drawers, it's an excellent footrest and it's easier on your back. You also may find that if you sit facing forward, it's easier on your back and your neck, because I care. No space in here to do that. All right, so I have posted the eChem lab. It's not like it's this massive secret. The questions are already in your post lab anyway. You had 5 attempts. And so we want you to start thinking about just the quality of it. You know what the questions are. They're already printed in your lab experiment. This is just how you turn in the lab report portion of it. So that's where that is. Just a heads up, if you've never noticed this about Blackboard, if you have a round circle next to a question, that means there's only one answer. If you have squares, that means there's more than one possible answer. So select all that apply. If nobody's ever pointed that out to you, that's the difference. Oh, make a note to yourself, because that's always how it works in Blackboard. Nope. All right, so I'm going to leave that. And apparently I didn't do very well. So I had it showing what all your choices are and how I did. Oh, dang. Okay. I'm sorry? No, it's in your lab. I had just neglected to enable it. Now, let's talk about the cheat sheet. The cheat sheet is also in here. And honestly, when I was taking your test, I just ran the numbers in my cheat sheet because I've done them. I know how to set them up. So I had to do all my calculations. Purpose of the cheat sheet here is so that, notice that it's popping up with things like, this is external, are you sure you want to enable it? Yes. It's a completely safe file. It's been used for 20 years at least. I created this file many, many years ago because I wanted you to be able to run sort of what-if scenarios. What if we change this? How does that affect our cell? So when you're choosing your cathode, it's a drop-down box. Notice that the drop-down box you can toggle down or up. You just have to be a little more careful to see how the arrow changes directions depending on where you're going, where you are in the list. So if I put it up towards the top, now I'm going back upwards. So let's say that my cathode is the silver reaction and my anode is the thallium reaction. It's going to ask you what was the temperature you're operating in. Anything that's yellow, you can type in. Any of the rest of the cell, you can't. For this cell, I'm going to need to know what the concentration is. And so it's just whatever numbers were when I was working with this the last time, that's the one it saved in terms of that. So what concentration of silver, what concentration of thallium-1. And notice, it does a calculation. This is what the N is for that half reaction. They both have to be 1 electron cells. N for this cell is 1, which means the N for my whole cell is 1. If I change this to the aluminum reaction, now it's saying, okay, well, my cathode now has 3 electrons in the process. Oh, look, that was one of your test questions. Aluminum ion plus 3 electrons makes aluminum metal. And your anode still only has 1 electron in the process. And so it has populated what N and E0 is. It's calculated what the mass action expression is based on these concentrations. So if you want to check your numbers, you can do it easily. It will only ask you things that will show up in the mass action expression so that you can check and see how you're doing with it. So this is the half reaction. This is the whole cell. And so you can figure out what the K for this reaction would be and all of those good things. So pretty easy to work with in general. Now that's the electrochemical cells when you're doing your wheels. For the reference data, that's just a list of all the things that you were going to need to know. I put that, honestly, that was for me. Reminds me what the half reactions are and what the standard cell potentials were. And then this cell references that. My recommendation, I don't think, yeah, you can't type here, so you can't accidentally overwrite it. So that when you get into this cell, then it will automatically ask you for just exactly what you need. So I made it so that you could only type in the cells that were yellow. Nothing this time. But some of the cells, for example, let's say that I did the hydrogen cell. Hydrogen cell is going to need two pieces of information. So I just left those cells highlighted. All right, lead storage battery, because you're going to need to type in whether it was a lead oxide or the lead, and honestly, I'm not going to guarantee that this is the right one. I'm just telling you that's what I put in. It's asking you to put in your temperature and the concentration of sulfuric acid, because that may have been different for you from one semester to the next. And what it's done here, honestly, is it's done the quadratic to solve for the concentration of hydrogen you would have in sulfuric acid, because it's a diprotic acid. The hydrogen doesn't, most of it comes from step 1, but some of it comes from step 2. So I did a lot of little math off to the side. And it calculates your cathode and anode and all those sorts of things. Big picture is this is for you to be able to check your numbers to see if you're on the right track. All right. So that's what the cheat sheet is. Again, it's so that you can very quickly check to see how your numbers turned out. Now, with the lab questions, our sample calculations come from the lab manual itself. It tells you I want to see for one non-standard cell. What does that mean? Has nothing to do with temperature. Has everything to do with what the concentrations and pressures are. So they're not at 1 molar. So I want you to choose a cell where the whole thing is not standard, so that concentrations are a factor. And you're asked to show me a sample of how do you calculate E cell, much like what you did on your test today. And so I just want to see you can pick any of the cells and do a calculation based on one of those combinations where it was non-standard. Oh, so one of your non-standard cells that you tested, because it asks you to compare your theoretical and your actual and that kind of thing. So questions about that? You'll bring me a hard copy of the final, right? Because I'll see you then. So that's all so you have a quiz to answer that's different questions. Now again, if you look at the quiz questions, it asks you things like, what would happen for this cell if the temperature goes up? So you can go back to your electrochemical cell, pick one that has iron. Come on. Yeah. So if you had an iron cell and you change you put in a concentration that's non-standard. Now what happens if I change the temperature? If you change the temperature, you'll be able to see what happens. That's why I did this, is so that you can run some what-if scenarios. If you had that cell and you change the temperature and you make it higher, what happens to the cell potential? That's what I'm asking you to look at. Well, since we've chosen our iron cell as our cathode, it would be this column, because this is the only one that we would be changing the temperature on. Exactly, because it only asks you to look at that one cell. So that's why I made that little cheat sheet, and it's it's helpful. to run that. Which of the following on the spontaneous cells? This is based on the concentrations you actually had in lab. And so based on what was available to you in lab, which of these would be spontaneous? So that's about it. All right, so questions about that? Concerns, prayer requests? So let us have a look at the last little bit of stuff. Everything else in this chapter is talking about thermodynamics and talking about overall spontaneity. Remember that spontaneity tells us that whether a reaction can occur without continuous input. Of energy. We said it also means that they tend to be efficient reactions, but nobody ever said they were fast. Most electrochemical processes are pretty fast, but if you're talking about the corrosion on your screen door, that's a fairly slow process. It takes years for it to fully oxidize and develop holes, or it takes years for something to rust through completely. So thermodynamics doesn't ever have anything to do with how fast it is. It can tell you things about whether it can happen. It relates to your K value, but that's it. So the only time we talk about speed in a chemical reaction is when we're using Faraday's equation. And Faraday's equation says that the amount of charge that transfers in a process is equal to the current that passes times the time. So current is in the unit of amperes, typically expressed with a capital A. And what an ampere means is how much charge. Coulombs are the unit of charge. So how many coulombs are traveling per second? This is something you would have to measure. Q is charge transfer. So when you're talking about electrolytic cells, it's not talking about the heat, it's talking about how much charge. And it would be nice if they used a different symbol, but they didn't. Because you're right, it's usually heat transfer in the thermodynamic application. So current is something that's either measured or you could calculate it based on data. And it tells you how much charge is passing in a given time frame. So Q here is charge, and T is time. And since amperes is in coulombs per second, then time in seconds is going to be important. Now, this is not the only thing that will give us charge. This is just coulombs, or Faraday's law, rather. This can be related to the number of moles of electrons that are transferred in the process. Typically, it's written as N sub E times Faraday's constant. And we already have discussed Faraday's constant. So if you happen to know the current, somebody's measured it or they've given it to you, and you know how much time has passed, then you could figure out charge. But if you know any three of these four pieces of information, actually you only need two of the three unknowns, or two of the three variables, because this is a constant, then you could find any of the other four. Now, I'm going to show this to you using the equations, and I'm going to show it to you using dimensional analysis. I personally don't usually use the equations, because dimensional analysis will also get you there. But let's see how. So when we use electroplating is when we apply electricity to a cell and we use it so that we can take some metal with some charge, add a certain number of electrons, and then make the metal out of it. You copper plate something or gold plate something we're taking the ions of gold and we're depositing it onto a surface and converting it into elemental gold. And so this process is always describing, or this equation is always describing a process where electrons are being transferred in some way. So the key thing first is always write your equation, because this is really a stoichiometry thing. Write the half reaction involved. We're trying to make gold from this. The only part I care about is the gold. So the only part of this that I care about is also the gold. What charge does gold have when he's in that compound? 3 positive. So how many electrons are going to be needed to make that balance? So in this equation, Ne is 3 moles of electrons. But that's per 1 mole of gold. So every time 1 mole of gold deposits, I'm going to get 3 moles of electrons. If I'm not making 1 mole, then it's going to be some portion of that. So the question says, what current, what is I, if I want to make this many grams of gold in 200 seconds? There's our T. So if Q is equal to IT, that's equal to NF. I'm solving for current. So number of moles of electrons times Faraday's constant over time should be equal to my current. So we need to figure out how many moles of electrons I'm going to get. What I know is that I want to have 3 grams of gold. And if I want to know about how many moles of electrons, I'm going to have to relate it to moles of gold. How do I get from grams to moles? Sure. Something like 197 grams of gold for every 1 mole of gold. But the question didn't want to know about gold, it wants to know about electrons. That's where I'm going to use that information. For every 1 mole of gold, there's 3 moles of electrons. Are you with me? So that gets me to moles of electrons. I know Faraday's constant, 96,485 coulombs per mole of electrons. And I was told the time of 200 seconds. So apparently 22 amps of current. So the key thing here is to remember what N is in that equation. N is moles of electrons. If you're given something about the metal, at some point you're going to have to relate how that metal comes from the electron. If you haven't written that half reaction, that's going to be a lot harder for you to remember to do. How much time in seconds? So we're looking for T. Does it take to plate 10.2 grams of silver using a 0.1 milliamp power source? So I know I this time. Need to write my half reaction. I have silver ion. If I'm plating it, what's the charge on silver? 0. No charge on something that's an element. So how many electrons? So there's going to be 1 mole of electrons for every mole of silver. So step one is write that reaction so that it's going to be really obvious to you. IT equals NEF. With knowing how much silver, I can find this. I know Faraday's constant. I'm looking for time. So I'm going to divide both sides by the current. And then substitute in. I have 10.2 grams of silver, but I need to relate the silver to the electrons. What's the relationship? Moles to moles, right? So I'm going to have to take grams of silver and relate to moles of silver. 107.9, I think, per mole. And for every 1 mole of silver, there's 1 mole of electrons. You okay with that? Substituting in Faraday's constant, 96,485 coulombs per mole of electrons. Now I got coulombs. Need to divide by my current. My current is 0.1 milliamps. Milli means 10 to the minus third amps. I'm dividing by it, that means multiplying by a fraction. And how does amps relate to coulombs? One amp is a coulomb per second. Here's how you can remember this one. Q equals IT. This is amps, this one's coulombs, this one's seconds. So an amp must be a coulomb divided by seconds. So if you can't remember it just right off the top, you can always plug in what you know the units have to be, and you can find your relationship as you need it. So coulombs are going to cancel, amperes are going to cancel. We're left in the units of seconds, which is reasonable for time. $10.2 divided by 107.9 times 96,485 divided by 0.1 e to the minus third. A lot of seconds. Basically 91 million seconds. It's going to take a while. So because we can't see the electrons, the way that we figure out how much is being how many are being transferred is by measuring the amount of the metal. So that's why we're always starting with some quantity of the metal, because that's our only indication that the process is taking place. We have 1.5 grams of chromium. What's the half reaction? If I'm going from chromium to chromium metal, how many moles of electrons? So I'm going to have to take the molar mass of chromium, and that will give me 1 mole of chromium. And what's the relationship between moles of chromium and moles of electrons? That's 3 to 1. Q is equal to IT equals NEF. We have a way to come up with this. We know this. The question wants to know how long will the process take? What are we solving for? So T equals NEF over I. Right now we've just figured out what moles of electrons are. You okay so far? So these are actually not that hard problems. They're just mostly plug and chug, but it does depend on your reading what the units are. If you're not paying attention to units, it becomes a little bit more challenging. How do we use this? Well, one way that we've done it is if we're actually plating something out. I have a piece of iron, and I dip it into a solution that has silver ions in it. If I make this negatively charged, because I've hooked it up to a battery, so this is an electrolysis situation, I've hooked it up to the negative lead of my battery, then what's going to happen is the silver is going to be attracted to that, and it's going to deposit out on the iron and coat it. Now that said, something else has to be giving those electrons up. So if I have this cell in place with a battery, it's the electrons are actually coming from this reaction. But usually when we do an electrolysis situation, we actually do it all in the same bath. So what we commonly would do is use a silver electrode over here. Because if I think about it, maybe this is a teapot here that we're going to use as our electrode. We put a little wire on our teapot because we want the silver ions to come to this. Remember, if the silver ions are being reduced at the cathode of this electrolytic cell, that means that the other one is going to be oxidizing to make silver ions. So I'm constantly replenishing my silver supply. So I want to start with a very super pure version of silver to create my silver ions that can then coat on my iron teapot. So if you actually look at a teapot, they're iron underneath if they're silver plated. Now you will find solid ones also, but they're a lot more expensive. So if you have silver plate, that's how they do it. And so your textbook describes a couple situations where they've actually used this to use electrolysis industrially. One way is to purify copper. One of them is to make sodium hydroxide. Actually, let me go ahead and pull that up so we can talk about those diagrams. Just blown my second attempt at that quiz. Dang it. Aluminum is something that we use very casually now. Until, I want to say, the late 1800s, I want to say the Hall process was like right about the end of the Civil War. Aluminum used to be extremely expensive. And the reason it was expensive is that it was very hard to retrieve the aluminum metal from the ore that it comes in. It comes in a form called bauxite. And so when Hall figured out how to do it, then aluminum became dirt cheap. And so now you can get aluminum foil at the grocery store and nobody pays any attention to it. What he figured out was that you had to melt the bauxite, the aluminum oxide, which takes a lot of energy, but you can do it. And so you take this molten bauxite and you put it in a substance called cryolite. And the cryolite is really just another source of ions because we want our electricity to conduct very well. And if you have lots of extra ions, then your supporting electrolyte is supplying those so that it will conduct pretty efficiently. And so then they just dip in carbon electrodes and the aluminum is reduced to molten aluminum. And so the aluminum forms a layer at the bottom and they just drain it off as they need it. And so it was a very, very tedious process. I don't know why nobody had thought to apply electrical current to it before, except maybe the electrical current was not as readily available until that time, really. We mentioned briefly the idea about when we were doing our plate. If I want copper to plate on something, then it's very helpful if my anode, the other half of the reaction, is copper metal. Now, that's exactly what they do. They take a cathode, and the cathode is hooked up to a battery. That's why it's negative. So it's taking the sign of the battery pole. And the copper ions are attracted to the negative pole, and they deposit on the surface. It just happens that then the copper is dissolving and forming the copper ions. But the other metals that are impure tend to form a sludge at the bottom. They tend not to go into solution as well because it takes a lot more energy to make them into ions. Let's think about that for a second. I don't know where it went. Sometimes it just does whatever it does. Where'd it go? Try it again. Fine. When you are collecting metal from a source, it's very common that you're going to get more than one metal. It's hard to get a really pure sample of a metal. So here we have a sample of iron. What they do is, essentially what they do with the Hall process, they melt it and it forms layers in the bottom of the container as they're reducing it to form the metals. If there's different metals, they'll form layers. And so they'll skim one layer off and then skim the next layer off, and they collect those metals. But there's always a little bit that didn't quite settle away from the other layer. And so that's why there's usually a little bit of something else here. Now here we have copper, mostly copper, maybe it's 90% copper, but there's a little bit of silver, a little bit of gold, and a little bit of platinum. What we're trying to do at our anode is to take this and make it into copper ion. And we're trying to take silver and make it to silver ion. Or actually, we don't really want that to happen, but that's a possibility. Gold could go to make gold ion. Usually it goes to gold 3, but it could be gold 1. I don't even know what platinum does. The cell potential for this one is 0.337. Cell potential for this one is about 0.799. I don't know copper off the top of my, or silver off the top, or gold. Try this again. I don't know gold off the top of my head. However, we have already an example. We want this to be our anode. In an anode, you have oxidation taking place. And your anode should be the most negative of your choices. Would you agree to that? So when I have this metal that is a mixture, selectively, this is the least likely cathode. Selectively, it's the most negative of my choice. That's why the copper selectively goes into solution, and the other ones just stay now as whatever metal they really were. And they call that the sludge. So now they've selectively, by dissolving the copper, by oxidizing it, they've now effectively removed the copper from that sludge mixture, because they just don't give it enough energy for the silver to do it. Oh, they just coexist. When you have a copper mine, your copper ore is not pure. And so, like I said, they melt it, they apply electricity, and they collect the layers, but it's not 100% effective. So then they do a second step that's just this. And by adjusting it so that there's not quite enough energy for this one to go, they give it just enough energy for this one to be oxidized, and then it selectively will leave and go to the into the ion state. And then they collect that copper on the other electrode, because it's the only metal ion in solution, so it's going to be the only thing that deposits at the cathode. So it's actually a very clever concept, and so that's how they refine metals. And that is it. So what do you need to do going forward? Like I said, I have a couple of exams to finish grading, and then I'm done with that. You have your key for exam 4, and I'll finish it in the next couple minutes. You know, you get a note card, 3" by 5". I would review first old exams. If there's anything you don't understand that came from an old exam, you know that the keys are there. I did update Piazza yesterday, day before yesterday. So that you now have link for exam 5. It has the links to all the individuals. Why might you want all the individuals? This is why. Let's say I want to go back to exam 1. It tells me which day it was we were talking about what topic, so that if you want to go to your playlist, you know which day to look for to find that topic. That's why I do the lecture links. I also collected all of the exam keys. Obviously, I hadn't put up today's yet because I just scanned that in a couple minutes ago, but y'all have a copy of that now. So all of your playlist here for all the videos if you want to go back to any of those things. So go back to your old tests, look for major problem types. If there's anything that you don't understand, you can go back to the playlist and figure that out, at least to find which day we talked about it, and you can review that idea. I would be looking for key problem types and key concepts. So that's really what I tried to hit when you were taking your exams. So you get a 3 by 5 card. I also made a note that your exam is on Monday from 12 to 2. It's not your normal class time. The exams are not usually the correct day, or the correct time. So 12 to 2, same classroom, yeah. So just a heads up on that. Trying to think if there's anything else that you need to know. Yes, it's the same format, it's the same length. If I had to do a titration curve, I wouldn't have you do 5 points. I might have 2 points on it. In fact, I can guarantee you're going to see a titration curve. That's one of the major problem types out of the second exam. So it wouldn't be as many of them. It's the same length exam. And it's just selected types of problems to see if you're on top of that. So be working on your note card. You will find that the process of actually making the note card, many students don't actually need it after that. I'm not going to guarantee that. I'm not going to, it's going to be the same format. So not very many multiple choice, but you will have some, because those tend to be where the big concepts show up. And then, so it's usually, I usually give maybe one problem, but it could be a multi-part problem for each exam cycle. For example, you could have, well, you can have the same reaction system, and I have you calculate free energy and K, and it happens to be a redox reaction, so now you can find E cell and that kind of thing. So it's going to be the big major types. You can guarantee you're going to see a Faraday's law problem because you hadn't been tested on that part yet. And the question that we had last time was, what's going to be your cathode, what's going to be your anode? You guarantee you're going to see that. We said if you have to have a choice, if you're just dipping electrodes into a solution, the solution's going to do what it's going to do, regardless of what you wanted it to do. Now, it may be that its best choice is still not going to happen unless you give it a lot of energy. It may need a battery. But the cathode typically is going to be something that's a cation, could be something that's a nonmetal. And who's the major competitor? Water. Your anode typically could be an anion if it's monatomic. It could be a metal and water. If it's a polyatomic ion, polyatomic ions could be either. So you just need to see if it's on the list somewhere. Check it on the left, check it on the right, because polyatomic ions could be either. Some polyatomic ions are neither. But for example, nitrate, we saw in one of our examples, nitrate actually is a fairly good cathode. We saw that up here.
Unless this lecture is going to be posted, right?
Yeah, I think it already is, unless I missed it. So yeah, you definitely are going to need to be able to make that distinction, because I want you to be processing what is the most likely outcome in a mixture. You can guarantee you're going to see a buffer problem. You can guarantee you're going to see, of course, your buffer problem could be part of the titration curve, right? Because that would be one leg of the titration curve. Any other questions, concerns, or prayer requests? So, go away. I'll be in my office. I did. Go away now. We're done. Yeah, I will. I'll be in my office till just before 5. I got a night class, and so if you need anything, that's where you'll find me.
Great.
Yeah.
You can tell me what's wrong.